Okay, so we're just we're looking at the randomized block design. We want to finish this chapter. We only have a couple of things left to finish. And so we were looking at the randomized block design last time. This is when we don't just have treatments and air, we also have blocks. And these were the formulas that we used. And this was our ANOVA table for the randomized block design, right? And we can get two tests, an F test for the treatments and an F test for the blocks. And that's how we get those, right? And we test the treatments by assuming that we hypothesize that all of the means are equal. And the alternative is at least two of the means are different. Right? And it can be all of them different, two of them different, or just some of them different. And we have that decision rule, reject the null hypothesis if the observed F is greater than the critical value. So we really know that rule, right? And we can also do we can hypothesize for the blocks that all their means are equal against the alternative, at least two of them are different. Can be all the population means, some of the population means, or just two. Same rule, we don't make anything up, we keep everything consistent. The decision rule is exactly the same. We reject the null hypothesis if the observed F value is greater than the critical value. The observed F value comes from our ANOVA table right here, from the data, these ones. And the critical value that we put a little star with it because it comes from the actual table. From here, the actual table, right? The theoretical values, right? So we looked at the example with the price of gasoline. We had treatments where we had different cities. We had Vancouver, Toronto, Calgary, Saskatoon, and Montreal. And we know that the price of gasoline varies from city to city, but we also know within the cities, price of gasoline can vary from brand to brand. Petrocan is different than Esso or Costco, right? Canadian Tire, and so on. So those were our blocks. The blocks were the brands. So you just organize your data such that you have columns of cities and your brands are in the rows. Those are your blocks. Yep. And we did this. We tested the treatments, which was the cities. So the treatments are the cities. Okay. And we found that the F is greater than, and so we rejected that the means are equal. Our hypothesis, right? Our hypothesis was they were equal. And so we conclude then at least two cities have different average price. And for the blocks, that was the brands, we concluded, interestingly enough, we concluded at least for these data that the means of the brands were not different. They were statistically not significantly different. So we could not reject the null hypothesis. We assume that they're equal. Right. We did another example here. It was just based on raw data. P was 6. That means the number of columns. B was the blocks. There was 10 blocks. That would be 10 rows. And then you just fill out your chart. If you know the sums of the squares and you know the degrees of freedom, you can get the mean squares, right? We know that pattern, right? So we take 2477.53, we divide it by 5 because it's the same row, and that's how we get the mean square for the treatments. We do the same thing. If you know the sum of the squares for the blocks, and you know the degrees of freedom, you can get the mean squares. And same thing for the error. So with today's quiz, we were given the mean squares. It was just a regular, completely randomized design. There was no blocks, but still we were given the mean squares and you had to reverse engineer to get what the sum of the squares were. You just work backwards. So for this test, we tested both the treatments and the blocks. And we concluded both that we could not reject the null hypothesis because the F value was not greater than the critical value F from the tables. Right. We also seen here, we had 45 degrees of freedom. Our table does not have a 45 degrees of freedom for the denominator. So we always round down, we use 40. We use 40 degrees of freedom for the denominator. All right, and that brings us right to this slide here. This is where we kind of finished. So what is the mathematical difference between the one-way ANOVA and the completely randomized experiment and the randomized block design? So what's the difference between those two? If blocks are ignored, all block variation is absorbed into the error term of the one-way ANOVA. So if you start from the same raw data, the design is if the design is balanced, then the sum of the squares for the treatments will be the identical for both treatments, but the one-way analysis for the sum of the squares of the error will be the sum. It will be the sum of the squares of the blocks and the error together. You would add those two from the randomized block. So if you went and had to do that, you could easily do that. Right. So for example, we go back to here to the gasoline prices, we could just ignore the blocks. Let's say we don't care about the brands. We just want the treatments. The treatments would just be equal to the sum. If you just wanted to make it a one-way analysis, you would add the sum of the squares of the blocks and the errors, and it would all become the error. And then you divide by the degrees of freedom and you get those new mean square error. That it would be a new mean square error. All right, so let's keep going. So this is another example that I use. It's taken from real data that's still live. It's collecting as we speak. I took a snapshot of the world in 2018, 175 countries, and then I organized them by continent, where there are 6 different continents. I think I ignored the Antarctica there, so, or I think I lumped them into Oceania. 1, 2, 3, 4, 5, 6. Yeah, 6. So I ended up getting these from the World Bank data for the 6 continents, and we can assume the continents, the groups are independent. That means no more than one country is in 2 continents. Every country's in only one continent. That makes them independent. Okay, so here's the data summary table here. I don't know why I was surprised by this. There are 51 countries in Africa. It's our largest continent. Asia, 47, second place. Europe has 39. I was actually surprised North America has 19. South America has 11. Oceania has 8. So they're counting all the little islands for North America, the Bahamas and the Caribbean. So then I calculated the life expectancy for each to get the average for each continent. So the average life expectancy in Africa in 2018 was 65 years, 65.3 years. For North America, it's 75.27, and so forth. And again, these are continuously getting updated. They kind of bubbled during 2020, 2021 from the pandemic, but then now it's back. I could probably update this now with 2024, maybe even 2025 soon, because we're now in 2026. But yeah, this is a World Bank data that is constantly collecting this data and analyzing life expectancy. And the data is showing that it's getting better. We're living longer, and it's, yeah, just in 200 years, it's really, the trend is very good, in the right direction. And becoming richer too. We study income and life expectancy. Okay, and it has the standard deviation. So I put all this into the box that you guys have seen before, right? You've seen those, and you can see that Africa looks like, for these data, it looks like it's significantly different, right? Seems to be significantly lower. Is it statistically different? We run the test to find out. So what we do is we check if all the means are the same for all of the world, all of the continents. And that's what we're gonna do. So does anyone remember what the line in the box plot means? Anyone remember? What does that mean? Anyone? Yeah. It's the median. Yeah, it's the median. So we can kind of use it as a rough guess, right? So we have some outliers. I think Africa, can't remember, there was one, there was Haiti in North America that was really low. Haiti was one of them. South America had one that was low too. So we'll just look at this test. So we run an ANOVA test to see if the means, life expectancies are the same for the world, for each of these 6 continents. The alternative is at least 2 are different. Again, it could be all of them are different, statistically different, or some of them are different, or just 2. So we just run the test, we're checking between the groups. That's the variability. We compare the life expectancy for each continent to a global mean life expectancy, which it was 72.7 years in 2018. I believe it's now close to 73, or maybe it's hit 73 globally. That's the life expectancy. Variability within the groups, that's when we compare life expectancy of individual countries to their continent's mean life expectancy. So those are your 2 sums of squares. Right, we compare the between group and the within group variation. So between groups is between the continents, it's within the continents. And here it is here. So if we know this sum of the squares, we should be able to fill this all in. So the degrees of freedom for the continents, the treatments are the continents. So what would we have for degrees of freedom? We have 6 continents. What's the degrees of freedom? For the treatments? Anybody want to guess? Yes, 5. 5. It is. So P equals 6. So this is going to be 5 because it's P minus 1. And for within the error, so there was just to remind you, there was 175 countries and we have 6 continents. So that's going to be 175. So this is 175. And we're going to subtract 5, we're going to subtract 6 continents. So 175 subtract 6 is going to be 169. Right. And then the total is 174. The total is always n minus 1. We have 175 countries, subtract 1, we get 174. Now, how do we get the mean square for the treatments? We can just take the mean square for the treatments. We're going to take 48.27, subtract 8, divide by 5. And that will give us, and please verify, jump in and let me know if you get something different, please. And I'll just populate that up here. Right. And that's the mean square, the average square for the treatments. The mean square for the error is going to be, you just take that number 91.0 divided by 169. And I get 24.2071. And so we just go to 4. There. And then we want to do the F test. The F observed, that's the F test. It's going to be the MST, and always put the denominator, the MSE in the denominator. So that's going to be 965.96 divided by 24.2071. And I got 38.89 or 39.89. right? So 965.96 divided by 24.2071. 39, I got 39.904 if I want to be really picky here. That's good. Give myself some room. I get 39.904 if I want to be really precise, and it's good to be carrying to 3. If you don't see me carrying to 3, we need to be carrying to 3 for test purposes. We might have cut off the MST there too. It's important to carry to at least 3 or more. I'm kind of cutting some of them off, but we're going to get the same conclusion here because it turns out that the F star, that's the critical value, we're going to use 5 and 169 degrees of freedom. I don't think we have a 169 degrees of freedom. So what will we do? We have a 5, and we will just use we'll use our largest one. Just use, don't use infinity, just use our largest value. We want 169 here, but we go to 120. 2.29 will give us a good estimate. All right, so 5 in the numerator, 120 in the denominator. That's going to give us a 5, and 120 is equal to 2.29. And you can see from there what we can conclude. Well, is there a difference in the life expectancies across the world continents? How would you conclude? So we talked about this last week. Formulas are really important, and conclusions, knowing how to draw conclusions is really important. Those are the focus. The number crunching is sort of the in-between, right? So
it's larger than the critical.
So what do we conclude?
That there is a difference.
Yeah. We reject. Yeah, we're going to reject. We're going to reject the null hypothesis and conclude and therefore at least 2 means are different. So that means at least 2 continents' life expectancies are different. And as the data comes in, we keep updating this, keep testing, run the same test, the ANOVA, and to see if they might one day maybe be statistically equal. Right. So that's how we run the ANOVA test, the life expectancy example. It's sort of one more example to help you understand the test. And there's one last thing in this chapter. It's called Tukey. Now, Tukey is the same statistician who invented the box plot, the Tukey box plot. So he came up with this HSD. It's called the honestly difference test, significant difference test. And so after enough test has been performed, and if we reject the null hypothesis, right, we can further investigate with this test. So this is like a post-test, if you will. And the reason is we're going to test for significant differences between pairs. And this is how you do it. We have this little studentized QA right here, where alpha is usually, what is our alpha significance level usually set at? Usually, yeah, 5%, right? 0.05 or 5%. And then we have the MSE, we know that, we have that on our tables, and we divide it by n. So this formula here that we're using only works if all of the treatments have the same number of rows, so the same number of observations. We can't do this with the continents example, the life expectancy example, because each continent had a different number of countries. But we can do this with the first example of this chapter, which was the 3 plants with the different ages. So we're gonna do that, because we concluded with that example, the plant example, that there was a significant difference. So we'll see which 2 plants. So there was 3 plants, right? We concluded there was a significant difference in the ages. And you can then just put in plant 1, subtract plant 2 for X bar and X by sub I and X bar sub H. And then plus or minus, it's your confidence interval with that little Q alpha. It's another table, but it's only used for this test. It's only used for these tests or confidence interval. And then you just multiply it by the square root of the MSE divided by N, which is this N is going to be, it's the number of observations in each column, in each treatment or column, if you will. So for the critical parameters, the little q, we have 2 degrees of freedom, not to be confused like F. These 2 degrees of freedom is, the first one is the number of treatments, which is P, right? P, number of treatments. And it's the second degrees of freedom is the air, it's the same as the air degrees of freedom. You just plug it in, those are your formulas, and you plug it in and you can see who would be different. So the table, let's do this. So recall that we rejected the null hypothesis in the employee's age example, and we resulted in at least 2 of the plant mean age are statistically different, but which pairs? And we'll check and see if the plant 1 and 2 are different, right? So what we do is X bar 1 equals 32, it was 28.2, I believe. You can check this for me. And 2 was 32. Does anyone have their notes from last lecture to verify that those are the means for plant 1 and plant 2? Yeah, thanks. We'll just compare these ones. It's going to be on 3 and 12 degrees of freedom. 3 because there's 3 plants. That's the number of treatments. 12 because it corresponds to the air. Right? It corresponds to the air degrees of freedom. Did we get those correct? Great. So how do we get this here? We need to get this Q value. It's called the HSDQ table. And it's just coming up. And it's a studentized table, and it's literally only for the Tukey test. And we said the numerator would be 3 because there's 3 plants, right? So that's treatments. So it's the number of treatments. And the bottom one is going to be the mean square error. It's going to be 12. So it ends up being 3.77. Right, 3.77, that's our value that goes into our confidence interval. We just come back, we'll go 3.77. So I have a decimal there. Get it really clear there, decimal 77. And it was 28.2, I lost my 2. So now we have everything we need. We just do this, we go, okay, we're gonna take X bar 1, plant 1, subtract 2, plus or minus this Q, right? Alpha, which is going to be 0.05. By the way, we know it's 0.05 because it says right there. That's what we usually use for all these tests, 0.05. Okay. And then we just plug these in. This is going to be the square root of the MSE. We get that from our ANOVA table. And so this is going to be the absolute value of 28.2 subtract 32, the absolute value, plus or minus 3.77 times the square root. And if you look back on your notes, the mean square error for that ANOVA test was 1.63. 1.63, then we divide by n, which is 5, because there was 5 employees at each plant. Yeah. And then we get an absolute value of 3.8 plus or minus. And again, we're going to be looking for a 0. It's going to be, that's why we spent so much time on the chapter 11, because we're going to look for this 0. So 3.77 multiplied by the square root, 1.63 divided by 5. The margin of error is 2.153, right? So if the calculator says 2.525, then we round to 2.153. Okay. Just normal convention rounding. Be careful with that. Some of you lost a couple of marks on the lab 1 for rounding. So I'm just going to write it here. If it's 2.1525, that will round to 2.153, because 5 says go up 1. If it's less than 5, we go down, right? Just regular. There's lots of rounding. There are no real rule, but there's conventions that we use, and we just use the regular convention. There's other ways to round, I know, but we'll use this regular one. And so we need a lower and an upper bound for this. Okay. And we get 1.2. $5.953. Are they significantly different? Are the ages of plant 1 and 2 significantly different based on this confidence interval? No. Yes? No? How many think yes? How many think no? Let's see. What should we do? How many say yes? There is? Yes, that is correct. Because 0, right? Since 0 is not in the interval, we conclude the means are different. Statistical difference between the two, between the average, the ages between plants 1 and plant 2. Right. That concludes. All right. We're going to go on to the next chapter.